Now we're going to go to our next speaker. Andrew, are you ready to share your screen?
I'm ready. Yeah. Can you see that okay?
Yeah, we can see it. Yeah. Okay. Very good. Okay, now it's really my pleasure and honor again to introduce to you our second speaker, the next speaker, Professor Andrew Stuart. Andrew is currently a Brain Professor of Computing and Mathematical Science and Caltech. And before he joined Caltech about, I think 4 years ago, he held positions at University of Warwick, Stanford University, and Bath University. He got his PhD from Oxford in 1986, and then postdoc at Oxford and MIT. He has made many fundamental contributions to numerical analysis of dynamic systems, application of stochastic ordinary and partial differential equation, etc. He has been an invited speaker at the ICIAM and also an invited speaker at the International Congress of Mathematicians. And Professor Stuart has won many other awards and recognitions. I think the most recently, been elected a fellow of the Royal Society. Andrew, please, you have the screen.
Thank you for the nice introduction, and thank you everybody on the organizing committee for putting together this meeting. It's been worth waiting for, even though it's been a tough 9 months waiting. So the topic of my talk is supervised learning between Banach spaces. And before I launch into it, I just want to explain why that is an interesting subject to study. As Ingrid and Jinqiao have both pointed out, deep learning and supervised learning in general has been very successful in a number of applied tasks, mainly in the data and information sciences. But there are many problems that are familiar to us who work in more mechanics-based science and engineering problems, in which supervised learning is naturally posed as a problem to learn a mapping between spaces of functions. The data that we're given is often in the form of an input function and an output function, and a large number of pairs of such functions. And what I want to do in this talk is take the viewpoint of studying supervised learning to learn mappings or operators between spaces of functions, and more generally between Banach spaces, to look at some of the mathematics associated with that, and to show how this might be useful within applications. And there's one basic take-home idea that I'd like to just emphasize right from the beginning, which is that, and this is an idea which is useful in many areas of computational mathematics, in optimization, Monte Carlo Markov chain, for example. And the perspective is that one should think about this task on Banach space before discretizing, and understand what the issues are when one thinks about supervised learning between Banach spaces, rather than simply discretizing and applying standard learning methods between finite dimensional spaces. So what I'm going to do is I'll set up the problem as I'm going to consider it, and I'll describe two approaches, one based on model reduction approach, which will correspond to an approximation in a linear space, as I will show you, and then a kernel network approach, which will be a form of nonlinear approximation. And for each one of these approaches, I will describe an application, the first one to crystal plasticity, and the second one to incompressible fluid flow. The work is collaborative with many people, and I'll show you who they are as we go along. And I'd be happy to make the slides available through the conference website, from which you'll find all the references and so forth. All right, so this is the setting in which I'm going to work. We assume the existence of an input-output map psi dagger, which takes one separable Banach space X into another Y. And we don't know psi dagger necessarily, but what we do have access to is data characterizing psi dagger. So pairs of points, xn, yn, with X in the input space X and Yn in the output space Y, and they are supposed to be related by yn being psi dagger of xn or some approximation of that. And I will assume and discuss later the relevance of the input data being distributed according to a measure mu. And then the goal, of course, supervised learning is basically approximation theory. The goal is to approximate psi dagger from data from within some class of approximations. And I'm going to look at an operator class, which will be a function from x cross theta, theta the parameter space in which we'll be searching for the best approximation, into y. And the goal is to choose an element theta star in theta, so that from our approximation class psi, we make a good approximation of psi dagger. And the basic principle, which I've already described when discussing the first slide, was that the viewpoint I'm going to take is to design the architecture. That means identify the operator class, design that on Banach space before discretizing. And that's an enormously powerful idea, and I can't emphasize how useful that way is to think about problems in many, many areas, and I believe that it will be useful in this specific area. Right, so let me just start by giving an example and explain some of the issues. So I'm going to look at a simple elliptic partial differential equation, a divergence form, and the information, I would normally call it data, but I want to avoid that because data means something different in this context. The information given to us to solve this problem is typically the source function f, boundary data, and this diffusion coefficient a, and one wishes to compute u. And just to be specific, I'm going to take the perspective that the operator of interest here is the mapping psi dagger from the coefficient a, which is in some subset of L infinity, into the solution space U in H1. And throughout this talk, both in terms of analysis and numerics, I will compute a relative error. And in this particular case, when we approximate psi dagger on the basis of data from the operator class, psi, we'll look at the average of the relative error at the optimal choice of parameter theta star. So in this particular problem, we actually have the partial differential equation. So in some sense, psi dagger is known to us. But I emphasize that the methodology I'm going to develop will only take data which is derived from this equation and will not directly use the equation itself. So that's what's called a non-intrusive method and would apply even if we did not know the equation. All right, there's been a lot of work at the PD neural network interface, and I can't cover all of the history in this talk, but perhaps an important distinction to draw for this talk is the distinction between finding a single solution of a partial differential equation described by a neural network versus learning from the PDE an operator which is defined by the partial differential equation. And in that context, I want to mention these three papers, and in particular, this nice paper of Zhu and Zabaras. And in that paper, which applies to the problem that I showed you on this slide, Zhu and Zabaras design a particular architecture having discretized the partial differential equation on a mesh of resolution 50 by 50. They design, therefore, an architecture on a finite dimensional space Rn, found by discretizing the problem. They optimize that architecture and they get a relative error of less than 2%. The relative error defined in this way that I describe here. So that's a success. However, if you take this methodology, and take the same architecture and then train it on different levels of resolution, you find that the test error increases. So the point here is that this approach in which one first discretizes and then applies standard methods from supervised learning, this approach does not enable us to move smoothly from one level of resolution to another. The intellectual capital that you invest in designing a good architecture here is not useful if you encounter the problem at a different level of resolution. So the approach that I want to explain to you in this talk is a different one. Rather than designing the architecture at a particular level of resolution, I want to design the architecture on a Banach space and then discretize the problem. And in doing that, the intellectual capital that we put into designing the architecture will transfer between different levels of resolution. And what you'll see is that with the approach I propose here, this blue curve will become flat. It will become constant with respect to resolution. So what we learn at one resolution is useful at another resolution. Okay, something to understand for this talk is that this is not classical numerical analysis where I'm expecting the error to disappear with the increased resolution. And that is because there's always a finite residual error based on the fact that we only have a finite amount of data. Okay, so you're not going to see that. I'm not going to turn this curve around and have it converge to zero, but by applying this approach, I will flatten this curve, and precisely because we will have learned something architecturally which is valid for the limiting continuum problem and not just for a given discretization of the problem. Okay, so that's the concept. And I'm going to describe two architectures, one of which leads to approximation in a finite dimensional space, approximation of the mapping between spaces of functions, and that's this model reduction approach. And then the second will be approximation in a nonlinear space. So this work on model reduction is joint work with my colleague Kaushik Bhattacharya, with Bamdad Hosseini, who's a postdoc at Caltech, Nick Kavatsky, who is a graduate student at Caltech. So this is the idea in a picture. We have an input space X and an output space Y, and our objective is to find psi dagger, which maps X to Y. And these X and Y spaces are functions, or Banach spaces in general. And what we're going to do is the following. First of all, we're going to identify approximate factorizations of the identity, which you can think of as autoencoders, on the input space X and on the output space Y. So the composition of G with F will be approximately the identity, but will pass through a finite dimensional latent space. Likewise, we'll do the same thing in the output space Y. And then we will approximate the mapping from X to Y by the composition of G with a mapping on the finite dimensional latent spaces, var phi, which we will learn using neural networks, and fx. Right, so that's a general approach to studying maps between spaces of functions and relies on three components. Two are computations using autoencoding to extract a latent finite dimensional space from the function space. And secondly, an approximation of a mapping on the latent space using neural networks. So in this particular talk, for the theory and computations I'm going to describe, the autoencoding is going to be done by means of principal components analysis. The methodology, however, is more general than that. It so happens that for the problems we have looked at, principal components analysis is the most effective way of extracting a finite dimensional latent space efficiently. So let me just take you through PCA in an infinite dimensional setting. We will in fact work on Hilbert space and equip the Hilbert space H with a probability measure nu, from which we can compute the mean under this probability distribution and the covariance C computed from the mean. And then principal components analysis works by computing the eigenfunctions and eigenvalues of the covariance operator C, and then defining a mapping F from the Hilbert space to the latent space RD, and a mapping G from the latent space back to the Hilbert space as follows. F is defined simply by taking the projection of H in the Hilbert space onto the finite dimensional basis constructed by the first D eigenfunctions of the covariance operator C, with these eigenfunctions ordered to be decreasing. Since C is a covariance operator on H, it's trace class, and therefore the lambdas, it's a compact operator, the lambdas tend to 0, and we can order them to be decreasing. So ordered to decrease, we project onto the first D components, and then G, which lifts up, just takes those VJs as coefficients in an expansion of an element of H in the basis made up of the first D eigenfunctions of the covariance operator. So we have an approximation space of dimension G, and we have an approximate identity factorization using the latent space RD, and it's an identity approximately in the Hilbert space H. So early work of Zwald, Bousquet, and Blanchard underlies the following two theorems, which quantify the errors. Firstly, the error in using principal components analysis, and then secondly, the error resulting from learning principal components analysis from finite data. So the first theorem essentially is an SVD-like theorem that quantifies the optimal subspace in the following way, as being made up of the tail of the sum of the eigenvalues. Remembering we have a trace class property, so that this quantity here tends to 0 as d goes to infinity. And then one can look at the error when one learns the principal components analysis from data. And in doing so, there's an upper bound which takes the intrinsic property of the measure and the function space H, and the error incurred there by finite dimensional approximation, and includes a Monte Carlo-like error for the learning of the eigenfunctions from data, and that scales as d over n. I'm now going to combine this with neural networks to get a theorem about an architectural approximation that works directly on Hilbert space. So what we will do is take this principal components analysis approximate factorization of the input and output identities, spaces, the identity on the input and output spaces. And firstly, we can define a principal components analysis using the exact var phi on the latent spaces. And then secondly, one can approximate var phi using a neural network. And one ends up finally with an approximation architecture which maps the Hilbert space X to the Hilbert space Y, and is made up of the composition of these three operators: finite dimensional reduction, neural network on the latent space, and then expansion back up to the output Hilbert space. So I want to make a couple of comments about this methodology and compare it to existing methods, such as the reduced basis method, which is widely used in engineering for problems of this type, especially with low dimensional input spaces. So there are two key points which are on this slide. The first is that our approach is non-intrusive. We learn the principal components analysis from data, and we learn the neural network from data, and we combine those three things, the PCA giving rise to G, Y, and FX, and the neural network. We learn them all from data in a non-intrusive way. In contrast, the reduced basis method is an intrusive method which requires repeated use of the partial differential equation. However, so that's a distinction between them. Both of them are, however, approximations that describe the mapping from Hilbert space into another Hilbert space through a linear approximation. That is, the approximation of psi dagger. The approximation is in the linear span of a data-driven basis, which can be computed in a number of different ways, including PCA for the reduced basis method or other approaches. But nonetheless, it's intrinsically a linear approximation, even though the coefficients depend non-linearly on x, the input function. The space is a linear space spanned by the phi j n. And that is also true for the approach that we are describing here, the non-intrusive approach based on PCA and neural network. All right, so the approach that we have proposed here converges. So this theorem describes what I mean by that. Given any epsilon, we can identify latent dimensions. They are a property of the measure mu against which we compute error. So we can choose dimensions and then an amount of data, and then a zero extended neural network, which by zero extended, I mean we compactify the domain on which it operates, with the property that the average error, in a manner that I'll describe in a moment, squared can be made less than epsilon, where we average over all input data distributed according to measure mu, and we also all input functions over measure mu, and we also average over the data assumed also to be distributed from the measure mu. So this is a fairly soft result in that we have not exploited in any way the use of depth to optimize the properties of the neural network as a function of the parameters such as the intrinsic dimension used to dimension reduce and the amount of data. Nonetheless, it does prove convergence, and it uses the basic result of Urotsky, which makes a connection between approximation of polynomials and use of ReLU functions. So I'd be happy if there are any questions later to discuss the proof. And if I do that, I will return to this slide here. The key issue that I want to draw your attention back to is that we have constructed here an architecture which is designed on Hilbert space, not on Rn. And it involves a combination of neural networks with an autoencoder, which in this case is based on principal components analysis. That methodology converges in the sense that if you take enough data, you can recover, or there exists a neural network such that one can recover an arbitrary epsilon approximation of the true map psi dagger. So I'd like to just show you that in operation on a specific example. So I'll return to the example I showed earlier. So this is the Darcy problem. Remember, we're interested in the mapping from A to U. And again, I re-emphasize, we're not talking about solving the equation for 1A. We're talking about learning the operator that maps A to U. So the example I'm going to show you, the A's are piecewise constant functions with contrast 4. And the interfaces are defined as the level set of a Gaussian random field that describes the probability measure on the input space A. And this is a typical, that's the permeability, and this is a typical output pressure field resulting from such an input. So what this figure shows, and this is the thing that I advertised at the beginning of the talk, is that with this way of thinking about neural network, we obtain an error which is independent of the resolution that we use to discretize the problem. That's in contrast to standard methods where one discretizes and trains. Here, we work out the architecture before we discretize. And what you see here is 3 different intrinsic dimension choices, 20, 50, and 70. And you see that the error is essentially constant with respect to the resolution used. This is the test error that I showed you earlier. So it's the average relative error averaged over the probability measure, which defines the principal components analysis. So by taking this perspective of learning the, defining the architecture on function space, we have solved the problem that was apparent in the very nice work of Zhu and Zabras, which, whilst they found a very low relative test error at 1 resolution, everything they learned at that resolution told them very little about computations at another resolution. In contrast, the method we are proposing, what one learns is transferable between resolution. And indeed, you can train the method on 1 resolution and then employ it at a different level of resolution with the parameters you train at the lower level of resolution. However, there's some care needed. As indicated in the theorem, one has to choose the intrinsic dimension D, which is a property of the measure mu on the input and output Hilbert space. One has to choose that to be sufficiently large and the amount of data sufficiently large. And the relationship between those requires some care and management as manifest in the theorem. So what you see here is that if you fix the amount of data, let's say we fix 1,000 data points, That means we solve the PDE 1,000 times for 1,000 different inputs and compute 1,000 outputs and use those as our data. If you plot the error as a function of the reduced dimension, that's the dimension used for the latent dimension reduction in PCA, you see this characteristic U-shaped behavior. As you increase the amount of data, the position of the minimum shifts to the right, but that reflects the theorem on the approximation capabilities of PCA based on finite data. All right, I want to show you the use of this method to study a homogenization problem that arises in plasticity. And this is work in addition to the collaborators I mentioned to you before, Kaushik, Nick, and Bamdad. This is also work with Birgitte Liu, who's a postdoc at Caltech, Zhongyi Li, who's a PhD student, Kamya, who is a professor at University of Illinois in Urbana, and Anima, who is a colleague in my department. So this problem, crystal plasticity, is a problem, gives rise to a nonlinear partial differential equation for a field U. And as with all problems in continuum mechanics, it is defined by a relationship between stress and strain characterized by the constitutive law P. And in plasticity, this is a law which carries memory. And the memory is usually described through what are called internal variables that are integrated alongside this dynamical model. We're going to study a homogenization setting in which one has small scale features in the material. And we are going to use microscale computations to define the constitutive law. And in particular, what we're going to do is learn a mapping, which psi-dagger, which takes the strain history on a computational cell. So these are small cells that make up the overall physical domain D. We learn the mapping from the strain history on the boundary. That's a function which takes values in the space of matrices, but it's a function of time, into the average stress on the cell. So that's also a function of time, taking values in 2x2 symmetric matrices. We train this model offline using quasi-static computations based on the level of a single cell, and then use that, the trained approximation to psi-dagger, to define our constitutive law. The reason for doing this, as I will show you, is that it leads to an enormous speed up in computational time for plasticity computations of this type, where one has multiple scales, 2 scales in this case. So to say in pictures what we're doing, at a small scale within the material, one has polycrystalline material of this type. And what we learn through the neural network is a mapping which takes us from the strain history on the boundary to the stress experienced on that cell. So what one sees here, the mapping from the top to the bottom, is described by a constitutive model that we learn using the principal components analysis-based neural network that I described theoretically in the first section of the talk. Now, a difference here between the problem that I described for Darcy, the Darcy flow, and the crystal plasticity, is that in this case, we had an input probability measure before that was known to us for the Darcy problem. It was part of something we could control. Here, the input probability measure is the implied probability measure on the space of strain histories on each cell within the interior of the domain D. That probability measure is not known to us. It's an emergent property of the solution of the partial differential equation. So that meant we have to address something known as transfer learning. We have to ask the question, what is a good probability measure to train on so that it will still be of value when we use the constitutive model that we've learned through neural network approximation on a problem which sees a different probability measure. And we found that by empirical work, that using random strain paths in the training gave rise to good approximations. So this is just what you see here on the right-hand side. These are the random strains on the boundary, and these are the implied stresses. And there are, in fact, in each one of these curves, two curves on top of each other. One is the truth, and the other one is the learnt model, learnt through the composition of principal components analysis with a neural network. And we tested in the localized cell setting how this training on a random input measure was able to predict correctly a number of simple stress-strain relations or stress-strain histories for problems such as uniaxial tension and loading and unloading problems. Again, the dotted curves are the approximation and the solid curves are the truth, and we see that we're able to accurately represent these phenomena, even though we are testing here using an input measure which differs from the training measure. So this is an empirical example of training learning, transfer learning working correctly. So we're then able to build that into the homogenization model and compute very rapidly, in comparison with pre-existing methods, complex evolution of plasticity. So in comparison with FEM squared, we're having a speed up of around 1 million. And compared with what's known as Taylor averaging, which is a good approximation in the setting we're working here with a large number of cells, we still see a factor of 1,000 speed up over that methodology. So there's much work that needs to be done here to theoretically justify what I'm showing you, but the potential in speed up, I think, is convincing. All right, so everything I've done so far, I've told you a philosophy, which is learn a neural network to map between Banach spaces and conceptualize it as a mapping between Banach spaces before discretizing. And I've shown you that in the context of what turns out to be approximation of the required operator between Banach spaces, approximation of that operator in a linear space. What I want to show you now is a different version of the same philosophy, which we call neural operator, where we learn what turns out to be a nonlinear approximation of the mapping, so approximation in a nonlinear space. But again, we apply the same philosophy, conceptualize on the space of functions and not having discretized. So let me just say a little word about the difference between linear approximation theory and nonlinear. So recall again, we're trying to find an input-output map psi dagger between two separable Banach spaces. And if we have a basis for Y made out of the span of the var phi's and a solution manifold M, which is the image of X in X under psi dagger, and that's in Y, then you can look at n-term approximation within this span. And you then get an approximation space, which is made up of the span of these vectors. So in the earlier example, this was the principal components basis. And you can then define what's known as the Kolmogorov n-width, which characterizes the approximation capability of the subspace for the manifold M. And for the principal components analysis that I've showed you before, the Kolmogorov n-width squared is bounded below by the tail of the eigenvalues of the covariance operator. Remember, the covariance operator on Hilbert space is necessarily trace class. So this number decays as n tends to infinity. This number decays to 0, but it may decay very slowly, meaning that the Kolmogorov n-width is limited by the use of principal components analysis as the basis of approximation. And this is a motivation for using a different architecture in which we have the opportunity to approximate the solution manifold by nonlinear approximation. And I will show you with Berger's equation that by taking this approach of nonlinear approximation, we can beat the PCA-based approximation capabilities that I've shown you in the first half of the talk. So to describe this architecture, I want to start by recapping neural networks in finite dimensions. And just want to say there are lots of variants on what I'm about to show you. And I've tried to explain things in the simplest possible setting to convey the ideas that underlie our work in this area. So let me start by describing classical deep neural networks as a mapping between Euclidean spaces. So I'm going to look at a mapping from X in Rm to an output psi. This is our approximation class in R. And I'm going to take the following form. There's some slight redundancy in this form, but it's to enable me to describe what we do on function space in a clean way. So the way I'd like to describe this neural network is as follows. We first have a linear layer that maps x0 to v0. And we then have an iteration where we take VL minus 1 and map it to VL using a sigmoid pointwise activation function applied to another linear transformation of VL minus 1. And then finally, another linear layer. Okay. There are lots of generalizations. I'm just describing a simple setting that is clean for exposition. So the set of parameters then are the set of matrices A0, A1, A2 up to AL plus 1, and the offset vectors B0 up to BL plus 1. So the approximation architecture is defined by this function class here. And in neural networks, one optimizes over theta to find the best approximation given data, and data will be in the form of pairs of points X linked in Rm, linked to output data in RR. All right, what I want to do is take the same basic picture, but instead of mapping Rm to RR, I want to map functions from Rn into Rm, so that's X, into functions from Rn into RR, so that's the space Y. And I'm going to do that by generalizing what you saw on the previous slide in the following ways. So firstly, I'm going to apply a pointwise operation, which applies for every Z in the domain D. So this is a pointwise. And then we're going to have a non-local operation, which looks just like the equivalent iterative layer within the classical neural network, except that I combine pointwise operation, again, with a non-local operation described as an integral operator with a kernel KL, and then have a linear output layer. Again, many generalizations. You can do pointwise neural networks on the input and output layer. But the essence of this is that we're mixing pointwise operations with a non-local operation in the form of an integral operator. And the parameters, therefore, are these pointwise operators, the ALs, the shifts BL, and these integral operators defined by kernels KL. And of course, to make this parametric and implementable, we parameterize these kernels so they become finite dimensionalized and constitute part of the overall parameter set theta, which defines this architecture. And our goal, again, is that we're given pairs of functions from the input space and the output space, and we wish to choose the parameters theta so that we mimic the mapping as expressed by those data points. So just to summarize, this architecture is made up of a combination of pointwise and non-local operators. The ALs are pointwise. Sigma is, as you know, in the standard neural networks, it acts pointwise, and the technical term for that is a Nemitsky operator, here described for functions x of z in X. And we have these non-local operators, which are integral operators. So this is a natural architecture, I believe, and those of you who work in this general area will recognize similarities with convolutional neural networks. An immediate disadvantage is the non-locality of the integral operator and the potential cost associated with discretizing this non-local operator, meaning that the evaluation of the neural network is potentially expensive as a function of the number of discretization points used to describe the domain D. And I'll return to that question in a moment. What I want to say is that we again have an approximation theorem for this architecture. And essentially the idea is in this paper of Chen and Chen. And there's a little extra work, lift that to the setting that we're describing here. So within this class, and with an architecture of depth 2, it's possible to find an epsilon approximation of psi-dagger mapping between spaces X and Y. And I want to emphasize and advertise the talk of George Karniadakis this afternoon at 1400 EST. George has also been working on approximating operators using neural networks. And indeed, his paper, which is paper 3C here in this area, also makes use of this work of Chen and Chen, which I'd like to draw your attention to and recommend George's talk. So the issue that I described prior to that theorem relates to the computational cost of the method. And we have broadly speaking, two approaches to that. One is graph-based, which I will briefly tell you about, and one is Fourier-based, which I will dig into in more detail. So in the graph-based approach, we're trying, so N here now is the number of points used to discretize the domain D over which the functions vary in the input spaces X and Y. So our approach here is to define the non-local operators on balls rather than over the whole of the domain D. So the integrals in the kernel integral operator defining the neural network are localized to integrals over balls in the physical space D. Nonetheless, this would remain an order n squared approximation, and it simply changes the constant. But we also use, one of the advantages of using a graph-based approach is it could work on unstructured grids and with unstructured representation of the domain D. So we use a graph approximation and Nystrom ideas to move between different levels of approximation. And we've developed a multi-level approach, which is order n. This is very much work of Zhong Yi, who is the PhD student I mentioned associated with this work. And so we have had some success with this approach. There's much to be understood from a theoretical point of view. It's primarily empirical. I'm going to concentrate on a Fourier space approach in which we replace the, well, first of all, we look at kernels which are convolutional and replace the integral operation by the composition of Fourier transform application of a linear operator in Fourier space and then Fourier inversion. We found this to be very effective on a number of problems, and this reduces the complexity to n log n, where n is the number of points inside D. So let me show you this for the Burger's equation. So the numerics I'm going to show you are for a value of viscosity of 10 to the minus 4, 10 to the minus 1, 10 to the minus 2. And we are looking at Burger's equation on a unit interval with periodic boundary conditions. And the map we're interested in learning is the map from the initial condition, the solution at time 0, to the solution at time 1. Okay, and this is a smoothing, because we have viscosity, this is a smoothing operator. And so this map can be viewed as a mapping from L2 into any HS space for any S positive. All right, so essentially we're trying to learn the solution operator for Burger's equation. We will have to equip U0 with a probability measure, and in this case, we look at Gaussian random functions from a Matern class. So this is a typical input and output for Burger's equation. I'm sorry, that should not say A, that should say U0, and this is U of 1. So this is the initial condition. And this is the solution at time 1, which, as you would expect with small viscosity, is forming an approximate shock. So what you see here is the relative error of a number of different supervised learning approaches. I just want to focus initially on 3 of them. So the relative error is defined as I've described earlier. It's the relative error between the learnt neural network and the true solution operator for Berger's equation in L2. And it's averaged over the Gaussian random field used on the input space, which is a Matern class Gaussian random field. And we're computing the relative error at a number of different resolutions of space. And remember that a key objective is to get resolution independence, precisely because we conceive of the architecture on the function space. So I want to just pick out 3 of these. So here, what in blue, FCN, is a fully convolutional network. So this is a standard neural network approach, which suffers from the issue that I described at the beginning. You can train it to do really well on a particular resolution, but what you learn about the architecture at that resolution does not transfer well to other resolutions, and the error increases. This is a log scale. The error increases with resolution if you take the same concept for how to represent the neural network. On the other hand, you can use the PCA method that I described in the first part of the talk, and you then get, firstly, a lower error. The orange is the PCA. So we've firstly decreased the error, but secondly, we've made it resolution invariant. So what we learn here is something we learn by conceiving of the architecture on function space, and it's not something we learn specific to any resolution. However, remember that the PCA is a linear approximation space. The Fourier methods, well, the neural operator method in general corresponds to approximation spaces which are nonlinear. And the Fourier neural operator is an example of that, which is also efficient because of the n log n scaling with respect to the number of discretization points. And you see that with the Fourier neural operator, we get even lower error than any of the others here. And we also get this resolution independence, meaning that what we learn at one resolution in terms of the architecture is relevant at all resolutions because it's an intrinsic property of the PDE and not of any one discretization. Okay, I'll just finish. I know I'm on end time. Just one last example to show the lifting of that idea from Berger's equation to the Navier-Stokes equation. So this is a Navier-Stokes equation in 2-dimensional torus. We use, therefore, vorticity stream function formulation. And we, in this case, have learned a mapping from the space of vorticity trajectories into themselves. So the input space here is the space of continuous functions on 0t, taking values in L2, mapping onto the same kind of object, but time translated and possibly lengthened. I just want to show you that this works. So across the top here, you have the DNS solution of the Navier-Stokes equation. And on the bottom here, you have what we've learned from the Fourier neural operator. And in eyeball sense, you see this is an excellent approximation, and we have much more quantitative numerical studies of that. So just to summarize, as was said right at the beginning in Jin Chao's introduction, neural networks have enormous empirical success in function approximation. Typically, this has been for regression problems from RM to RR, or classification problems where RM maps into a set of classes. What I've been doing in this talk is to discuss neural networks and generalizations of them as mappings between spaces of functions and more generally separable Banach spaces. Motivation being that many problems in science and engineering naturally are described to us and given to us in terms of mappings between spaces of functions. And the key idea that I've been trying to emphasize is that one should conceive of the architecture rather than discretize. And I've concentrated on architecture rather than training and optimization because I believe that as we learn more about architectures, issues with over-parameterization are going to become less important, and that the specifics of how people currently train neural networks are not necessarily things that are going to have longevity over a decadal timescale. On the other hand, the architectures that are coming out of neural networks, I think, are a place where there is a lot of interesting activity that can have impact over several decades. There's generalizations of this work to what are called random feature methods, and there is work here with Nick Nelson, who's a PhD student at Caltech, that show similar conceptual ideas in that context. The method we use here is purely data-driven, so that very much in the framework of other work that's been developed by Yanis Kevrakidis over the last few decades, and it's widely applicable. It's non-intrusive, so it can be used for PD problems, but also conceptually works when one is just given data in the form of functions, so time series, cyber physical systems, and so forth. There's loads of extra work that needs to be done in this area. This is just the beginning, and I've just mentioned a few there. Very grateful to you for listening. Thank you.
Well, thank you very much, Andrew. Beautiful talk. It looks like we have quite a few questions.
We have quite a bit of question here.
John, you want to start some questions?
Yeah, I would like to start, with one here is like, so this work, it's sort of in parallel, looks like a generalizations of sort of non-intrusive UQ method in a way, where usually in the traditional polynomial chaos setting, if you are trying to learn, a map between finite dimensional space, right, then you usually are bounded by the number of dimensions. But now what you're learning is actually space of functions, right? So your covariate functions now is actually space of functions. Now the question is like, when you really want to do this, like apply this methodology, right? How many data actually, how does this method depends on the size of the pairs of covariate and response? For instance, your stress path and strain path and your stress of the cell.
Yeah, I mean, that's a very key question about this general methodology. Let me talk about the PCA method, first of all, which is the one we used in the plasticity computations. You see from the theory there that there are very delicate relationships between the intrinsic latent dimension, the amount of data, and how that interacts with the way that one represents the finite dimensional neural network. The PCA analysis relating the dimension of the intrinsic space and the amount of data, I think, is sharp and shows already that one needs to carefully choose the amount of data in terms of the choice of the intrinsic dimension. And the intrinsic dimension itself depends on the probability measure in question. So that part is fairly well understood. The part that we've not well understood in our theory so far is the relationship between the depth of the neural network and how to optimally configure that with respect to the intrinsic dimension and the dimension of the data, the D and the N. In practice, we find that we can train very accurately using on the order of thousands of input data points using neural networks which have depth 4 or 5 layers for the PCA type methodology on a range of PDE problems, including crystal plasticity. But I think we're far from having a complete answer to the question. I don't think that we have an optimal theorem. And more work is needed to characterize that relationship between the neural network and the parameters D and N. And more work is needed, for example, in crystal plasticity, there's no proof that what we're doing is working because we have used a transfer concept. We trained the constitutive law on a probability measure, which is not the emergent probability measure that happens when you do a computation. So there are many, many open questions in the direction you suggest. Thanks.
So
wait a minute. Can I read a question from the chat group? You probably do the Q&A.
yes, I'm actually trying to read this. Go ahead.
Good is a question. Which error measure for Berger's equation? What happens to performance when viscosity equals to 0?
Yes, so very good question. So the viscosity in the talk that I showed in the talk was 10 to the minus 2. Things deteriorate as the viscosity goes to 0, as you would expect. We do show empirically that the use of the nonlinear approximation space that arises from the Fourier neural operator is empirically beneficial. Nonetheless, if one wants to go to very small viscosity and approach the conservation law limit, I think we would need new architectures to be able to do that adequately. And the same will apply, of course, for Navier-Stokes equation in the large Reynolds number limit as one approaches Euler equation. There's no way that I would claim that we have a good architecture for those limiting problems.
So again, what's the error measure? That's the first part of the equation, like error 1 norm or whatever.
Sorry, so the error measure is the relative error in L2. So
error 2 is a good measure for Berger's equation? No.
Yeah, so it's the relative error in L2 at time 1, averaged over input data taken from a Gaussian random field, which is of Matern type.
Okay, so here's one. If the PDE is given, can one exploit this information explicitly in the constructing the architecture?
Yes, that's a really good question. And the answer is yes. Let me give an example, which actually is easiest explained with the random features method, which I mentioned on the last slide. In the random features method, one looks for an approximation over a space of random functions mapping x to y. And if I could take the Berger's equation as an example, we constructed those random functions to build in the basic properties of Berger's equation. So the basic property of Berger's equation is that one has forcing or input data at large scale. One has a nonlinearity, which is energy conserving, but moves information from large scale to small scale. And then you have dissipation, which is predominant at small scale. And that's also true for the Navier-Stokes equation. So you have an understanding of the physical processes that are at play in the solution operator. So rather than using the equation directly, you can use what we understand about the equation to design the architecture. So in the case of the random features method for Berger's equation, we designed random features which have that property of working in Fourier space and describing the propagation from large scale to small scale via the energy transfer of the nonlinear term, and then removal of energy at high scales. So that's specific. More generally, the answer to your question, I would say in this area, is for these non-intrusive methods is to try and use intuition that we have from our mathematical analysis of the equations to design good architectures that encode mathematical and physical structure that we understand. And just one more point on this. When you have the equation, you also have the chance, and this is maybe different from standard supervised learning, we have the chance to choose the input probability measure mu. So if we generate data by solving the equation, we can choose which measure we train on. And there are interesting experimental design questions, which I alluded to in the crystal plasticity problem, concerned with how one chooses the input measure to get a map which is trained for the task that you want to use it for. So for example, in inverse problems, in different work, using Gaussian process regression, we learn about the input measure by an entirely different methodology and use that to define the input measure. And thereby we train neural networks which are accurate where we want them to be accurate, which in the case of inverse problem is close to the solution. So there are many things one can and should do to build in the specifics of your problem into the choice of the architecture and the choice of the design measure. Thanks.
Well, it looks like there are lots of more questions. Can I maybe combine some of this question, ask you a quick one here?
Yes.
You mentioned in the very beginning that you mentioned something like the given the number of data is finite, you are not going to expect in the traditional numerical analysis the error will actually go down. Did you say something like that? But if you take this Perth media, you can put an A, then you kind of get a U. You basically can solve that equation. You can estimate as many data as you wanted. And now if you increase the dx dimension of the latent space, what you call, use the PCA, then you have this number of parameters of the neural network. If you let both of them increase, go to infinity, would you see the error will drop to 0?
Yes, that's what you said is correct. So if all of those things go to 0, you can get the approximation as small as you want. But remember that those 3 parameters, the intrinsic dimension, which is a property of the measure, the number of data points, and the approximation capability of the neural network, all of that is defined on function space. So when so I can drive that error to 0. But the computations, there's an additional parameter, which is that the computations take place at a given level of resolution. So all I'm showing you in those computations is the residual error given a specific amount of data. So I haven't gone to the limit. And furthermore, I can compute that with different approximations of the partial differential equation on different grids. That's separate from the intrinsic dimension, which is a property of the measure. And so all of those errors that you saw that were constant with respect to mesh resolution, they were computing the error between the numerical solution at that grid resolution and the neural network trained at that grid resolution. And we did that for a bunch of different grid resolutions.
Well, that's thank you so much. I actually have many other questions. With our time is running out, Andrew, we can probably approach you some other way to ask you more questions.